Okay, so in part 2 of this video, because we found that the required depth is greater than 40 centimeters, which is our embedment depth of the post, we'll reconfigure the problem and use the S value in this case, so the strength per foot of depth of concrete. Now, we won't go through the actual calculation using replacing that S value for crystalline bedrock, which was 1200 psf per foot, with the S of concrete, which is much larger and will make the problem work almost regardless of what our embedment depth is. What we're going to do here is we're going to say if we want to use that value of S concrete, we need to use our engineering judgment and think about what's actually going to be happening with that concrete interacting with the post in the blockout. So as you can remember, the post is in a structural concrete blockout, and that blockout is within our ramp fill, which I'll use green for here. Now, the first thing we're going to check, and I won't go through the setup, this is the setup here for the standard F2 drawing, and it can be applied to any other standard fencing drawing. We're going to first take our moment about point O. So in this case, we're checking that the concrete blockout is bearing against this ramp slab. That's not typical for slabs to be used in this way, but drawing a free body diagram, this is the situation we have in which the blockout is being, let's say, resisted by the compressive strength of the structural concrete in the ramp slab. And as a note, we'll take F equals 1, so that isolated pole factor, we won't apply that anywhere here to be conservative, and we'll take our 10 megapascal value for the compressive strength of concrete. And about point O, we have our overturning moment, which is going to be here, coming from here, which is just assuming that the compressive strength of the ramp is acting at 1/2 the width of the ramp. So our overturning moment is our overturning moment is what is coming from our force on the post. So our overturning moment is going to be our P live load, which I believe is 328 pounds, acting at 1 meter from the top of the ramp slab, because that's where our point O is. And our restorative moment is going to be that 10 megapascals operating at 1/2 the ramp width. We convert it to kilonewtons per meter squared, and then I have in blue here that the area that it's acting on is just going to be that 15 centimeter diameter of the blockout multiplied by the depth of the ramp, and then it's acting with a lever arm of the depth of the ramp divided by 2. And then we're wanting to check our factor of safety ultimately, such that the returning moment over the overturning moment, is greater than 3. Which is also quite conservative, but because we are doing this check outside of the realm of code, just using our engineering judgment, we want to be really conservative here. And then we'll take our some of the forces, some of the moments about point L. Sorry for that, should be L. And our same overturning moment is occurring with a restorative moment. Now, our restorative moment we're going to evaluate a little differently, because at point L, we're now looking at the post bearing against that concrete blockout. So we're looking at the blockout, it's going to pull out or crush the ramp slab, and it's not. And now we're going to look if our post is going to crush our structural concrete blockout, and we'll see that it doesn't. But here, we're going to take that area that it's bearing on to be 40 centimeters times 5 centimeters, because that's the diameter of our post. If you refer to the standard drawing, you can see the diameter is about 4.8 centimeters. We'll round up to 5 of the schedule 40 pipe called out. And then the lever arm is going to be that 40 centimeter depth divided by 2 to get our restorative moment. And finally, we can take the same factor of safety, restorative moment over overturning moment should be greater than 3.